Hello, AP Stats students. Today we will finish up Unit 7 by doing 10.2C notes, significance tests for difference of means. Previously, we did confidence interval for a difference of means. For significance tests for a difference in means, an observed difference in sample means can reflect an actual difference in parameters mean 1 and mean 2, or it may just be due to chance variation. In random sampling or random assignment. It's really important that you write your null and alternative hypotheses in a specific form. And in this case, the null hypothesis would look something like this. So the null hypothesis, where the mean of the first group minus the mean of the second is equal to a hypothesized value. We are often interested in situations in which the hypothesized difference is 0, where there is no difference between the two means. And so we are going to use 0 for our hypothesized value, which would then make the null hypothesis look like this. So the null hypothesis, where mean 1 minus mean 2 is equal to 0, or the way I tend to write it, where there is no difference between the two means, so mean 1 is equal to mean 2. The alternative hypothesis is what kind of difference we expect, so if there were a difference. And so it can take on many forms. It can look something like this. So you can say the mean of the first is greater than the mean of the second group, or the mean of the first is less than the mean of the second, or even that they're different from each other. So if it doesn't specify. So just be careful with the wording when you're writing your null and alternative hypotheses. Also, it is very important, and students don't do this often, they get points taken off, is just tell what your variables represent. So mean 1 could represent women, mean 2 could represent men, and so on. Okay, so what would the two-sample t-test for the difference between two means look like? Well, the state portion, the same basic state that we have always had, test the hypothesis that the difference in the mean of blank and the mean of blank is 0 at whatever significance level. And there's your null. You can write one of two ways, and there's your alternative, and you can write it one of two ways, where the mean is the true mean of blank and the mean 2. So basically, you're identifying each group as well. And then always state the test that you're using. So in this case, you would be using a two-sample t-test for means if conditions are met. So the random condition, pretty straightforward. Normal condition, if the sample size is large enough, so n greater than or equal to 30 for each group, and you have to show the normal condition for each group, then the sampling distribution will be normal, approximately normal. If the sample is not large enough, so if it's not greater than or equal to 30, then you must graph both samples to check for skewness or any outliers. And the independent condition is the same as it usually is. The two populations are at least 10 times as large as the corresponding samples, and that the samples group themselves and the individual observations in each sample or group are independent. Now, the next thing you want to do is if the sample means and the sample standard deviations are not calculated for you, then you must calculate it doing a one variable stats. And next you compute the t-statistic. So the t-statistic, it's like a z-score, but it's a t-score because it's t distribution, sorry. So the t-statistic is equal to the difference in the sample mean, so x bar 1 minus x bar 2, It's minus that 0 because it's that hypothesized value. That's from your parameter, divided by the standard deviation, which is standard deviation of the first squared divided by that sample size, plus the standard deviation of the second divided by that sample size. And you take the square root of it, and that'll give you your t-statistic. Then you're going to calculate the p-value based on getting a probability of t, that value of t. So calculate the p-value by calculating the probability of getting a t-statistic this large or larger in the direction specified by the alternative hypothesis, HA. Compare the p-value to your significance level. Once again, if the p-value is less than alpha, we reject the null hypothesis. If the p-value is not less than alpha, we fail to reject the null hypothesis. And then we interpret what those results in context mean after we say we reject or fail to reject. If we reject the null hypothesis, we have convincing evidence of the alternative hypothesis. If we fail to reject the null hypothesis, we do not have convincing evidence of HA. And let us do one sample problem. In commercials for Bounty paper towels, the manufacturer claims that they are the quicker picker-upper, but are they also the stronger picker-upper? Two AP statistics students, Wesley and Maverick, decided to find out. They selected a random sample of 30 Bounty paper towels and a random sample of 30 generic paper towels and measured their strength when wet. To do this, they uniformly soaked each paper towel with 4 ounces of water, held two opposite edges of the paper towel, and counted how many quarters each paper towel could hold until ripping, alternating brands. Here are the results. So you have 30 results from Bounty and 30 for the generic. And so what I did was I entered Bounty in list 1 under Stats Edit, and then I did generic under list 2. Now, looking just at the numbers, it looks like Bounty has larger numbers, but is there really, are they really the stronger picker-upper? So we'll see. Use the significance test to determine if there is convincing evidence that wet Bounty paper towels can hold more weight on average than wet generic paper towels. So in the state portion, we will test the hypothesis that the difference between the mean number of quarters held by wet Bounty paper towels and wet generic paper towels is 0. That means there is no difference, but we definitely need to put at what significance level. And what we will do is, because we always use 0.05, let's just use an even smaller significance level, and let's use 0.01 and see what we end up with. Okay, and so your null hypothesis that there's no difference, and I'm going to label mine as the mean of Bounty is equal to the mean of the generic, and I'll identify those here in a second. And your alternative states that the mean of Bounty will be greater than the mean of the generic. So you can write it like this, or you can write it like this. Or you can just remember that this means the same thing, that there is a difference. Okay. Where the mean of Bounty is the actual mean amount of quarters held by Bounty paper towels. And the mean of G is the actual mean amount of quarters held by generic paper towels. If conditions are met, we will use a two-sample t-test for means. For the random sample, there's a simple random sample of 30 Bounty paper towels. And simple random sample of 30 generic paper towels. Normal condition, you must show both normal conditions. So definitely 30 is greater than or equal to 30 for Bounty. And 30, thank God, now we don't have to graph it. Okay, so both of those conditions are met. Excellent. And now for the independent condition, it's reasonable to assume that the Bounty strength does not affect the generic strength. Also, there are more than 300 paper towels for each brand. All right, now for the due portion. And notice none of the statistics are given to you, but these are already in my list 1 and list 2. And so I found the sample mean for Bounty, and it was 117.6. And the sample standard deviation of Bounty is 6.6. The sample mean of the generic was 88.1, and the sample mean for, the sample standard deviation for the generic is 6.3. And now we can calculate our t-score. So t is equal to 117.6 minus 88.1. So the way I wrote my alternative hypothesis, so Bounty minus generic divided by the standard deviations, or standard error, so that would be 6.6 squared over sample size, the first one, so 30, plus 6.3 squared over 30 square root. So that is 29.5 divided by 1.67. That gives me 17.71. So at this point, you want to find the probability that you're going to get a t value of 17.7 or greater, and greater because we look at our alternative hypothesis. So we will do a TCDF where our lower bound will be 17.71. Upper bound can be something like 100 or 1,000. Our degrees of freedom, well, both sample sizes are 30, and you always take, if they weren't, you take the smallest sample size and subtract 1. So in this case, our degrees of freedom will be 29. And that'll give us a p-value of 2.1 times 10 to the negative 17th. And that basically has 16 zeros in front of the 2, so it's essentially 0. And 0 is less than the alpha. So since our p-value is less than 0.01, we reject the null hypothesis. We have convincing evidence that wet bounty paper towels hold more quarters on average than wet generic paper towels. Now, you can do a two-sample t-test for the difference between two means on the calculator. So again, we like stat a lot. So go to stat and arrow over to tests, because you have edit, then you have calculate, then you have test. So arrow over to tests, and you are going to choose a two-sample t-test. We're going to choose either data or stats. Well, my data was already in list 1 and list 2, so I chose data. I entered the appropriate information, and then on a screen, you will get these values. So you will get and you have to write this down, what's on your calculator. So you write down your t value, t score, and my t was 17.64 that the calculator calculated, which is very close to the 17.7. The p value was 2.98 times 10 to the negative 25th, which is even smaller than what we got by hand. And then the sample mean of bounty was 117.6, and the sample mean of generic was 88.1. This is what it shows on the calculator, x bar 1, x bar 2, so I'll just leave it like that. And then the standard deviation of x1 was 6.64, and the standard deviation of the second generic was 6.3. There we go. And then, so that was the information given on the screen. You also would have to include some of this other stuff, so that you did a two-sample t-test using your calculator, and you did it using L1 and L2, and then you also had the mean of 1 was greater than the mean of 2, and I'll show this to you on a separate video. It is preferred to use a calculator on this particular test, on a two-sample t-test, and the reason why is that complicated degrees of freedom, and the degrees of freedom shows up as well. And again, I'll show you on a second video. Now, we are going to kind of conclude by just talking about using t-procedures wisely and just a little bit about normal conditions. So two-sample t-procedures are even more robust against non-normality than one-sample t-procedures. When the sizes of the two samples are equal and the two populations being compared have distributions with similar shapes, then probability values from the t-table are quite accurate for a broad range of distributions when sample sizes can be as small as 5. Now, we definitely want larger sample sizes, but they can still be accurate. When the population distributions have different shapes, larger samples are needed. For the guidelines, if the sample size is less than 15, use t-procedures. If the data in both groups appear close to normal, if the data is clearly skewed, or if outliers are present, don't use. For sample sizes 15 to 29, use t-procedures unless outliers are present or there's strong skewness. Oops, I can't spell here. Outliers. And for sample sizes 30 and larger, use t-procedures even for clearly skewed distributions. Oops. Graph. When planning, if you're planning your own two-sample study, choose equal sample sizes if you can. It basically decreases the standard error of the difference in means, making the power of the test higher. And who knows when you'll get to do samples, or if you're going into any kind of research in your careers, this would come in handy. As far as using t-procedures wisely, never use pooled two-sample t-procedures. And the only reason why we don't use them is because we use them for proportions, and we use them for doing a two-sample z-test. So remember, ZAP is for proportion, TAX is for means. So you use you use pooled data for two-sample z-test, and that is for significance testing, not for intervals. Right. Some software will give you a choice of two-sample t-statistics. One is labeled as unequal variances. This is what we use because it works all the time. The other is labeled as equal variances. It is a special case, so it only works for the special cases and is inaccurate for the other cases. It was commonly used before technology was readily available. So just use pooled samples for proportions, but not pooled sample for means, where t is involved. Okay. For inference for experiments. In experiments, we aren't sampling from a larger population, which can interfere with our ability to generalize to the larger population. In experiments, we have our volunteers. So we can still infer cause and effect. So as long as we do a random assignment with these volunteers. Don't use two-sample t-procedures on paired data. Remember, paired data we had when we had that matched pairs. For matched pairs, we would use the one sample paired t-test. That we used in Chapter 9, and that's one where you graph the differences. So paired data comes from the same individual or similar individuals. Beware of inference without randomness. So random sampling from a population allows us to infer to the population. Random assignment to treatments give inference to cause and effect. And that's the whole point of having these studies. And that is Unit 7.